Hey, so I'm going to be recording a video about Copernicus and scripting in Copernicus with Vex, OpenCL, and Python. I'm also going to be showing a little trick to use Copernicus as a renderer. I'm a little late to the party here. I've actually been taking a break from Houdini, but I'm coming back, and I like doing 2D effects, text art, and for that I need a lot of image manipulation stuff. So I sort of tend to always try and push any image manipulation thing I'm using to the limit, try and see what it's capable of. I'm not really going to be showing a lot of like real usable effects, but I'm showing different techniques for scripting specifically. So first of all, I'm just going to be showing rendering some text art. So here I have some text art. I just have a font, I'm extracting borders, resampling it, layering a couple copies on top of itself, and then using point jitter to make this kind of effect. And then to get this into the Copernicus renderer, I have to add CD. So I just add a white color here, and then I use polywire to make it 3D geometry. And you can obviously change around the wire radius a bit till it gets how you like it. And then I'm creating a CopNet here, and basically I do a SOP import to bring in that SOP geometry, and then a camera import, which brings in my camera from the OBJ level. And then I use rasterized geo here, and as you see, this sort of, well, it rasterizes it. It's like a render. I have to set, so when you create rasterized geo here, it's going to have like intrinsic alpha here by default. So I just want to change that to RGBA and then change name to C, or I guess CD in this case. And then that's all I've done here. And then, if I select my camera and I lock to it, I can move around and let's see, why is this not working correctly? Sorry. Let's fix around these connections. Right. So now I can move my camera and you can see kind of this rasterized version updating. So that's kind of cool. It's a lot easier to do it this way than to set it up with Mantra or Karma, because all I want to do is just render like, simple lines and colors. So this is way easier. You can also do this using, you can render the normal out. In this case, you can see I have this pig head and I'm just showing the normals. You can also do, for example, alpha for a quick alpha mask. Yeah, stuff like that. So that's pretty neat. Okay, let's go into Vex a bit here. So basically, I just have this file node here, just giving this default butterfly, and then I'm just going to put down a wrangle. And this is actually just a volume wrangle. So you can look at the docs here, and you have some variables available. IX, IY, the integer index of the current voxel. You also have resx, resy, resz, etc. So if I just want to do a brightening effect, so you have these inputs here, number of inputs, and then number one is set binding name C. So that what that means is the color is available in this at C, and since I've set the type to RGBA, this is a vector 4 here. So all I need to do is just multiply that by some brightness parameter here, and there you go. You can see how I'm, affecting that image with Vex. Just looking at UVs a bit here. So like I said, you have IX and resx. So UV is just basically the voxel index divided by the resolution. Here you can see that I have the kind of typical green to red to yellow UV image. Another way you can do UVs is using at P, which if we go in the composite view, you can see there's it's ranging from -1 to 1 and 1. So all we have to do here is just remap that to the 0, 1 range. You can either use fit 1, 1 or just add 1 and divide by 2. And yeah, just showing that's another way to get the UVs. So talking about sampling other pixel values and from other inputs as well. So a volume wrangle is kind of like a shader. You can only affect the voxel you're currently processing. And it's processing many voxels in parallel, which makes it faster, like a shader. Now, that being said, volume wrangle is on the CPU, OpenCL is on the GPU, but in effect, they're the same thing. They're still doing parallel processing. So even though you can only write to the pixel you're currently looking at, you can still read from other pixels. And to do that, you're going to use this volume sample function. Actually, specifically, it's volume sample p, which will return you a vector 4. If you just do volume sample, that'll just give you a float. And see, I have two inputs here. I have C and C2. For C, I'm just using the butterfly image, and for C2, I just have some fractal noise, which is the same size. Inside my snippet here, I'm reading the noise value using volume sample P. I'm using @P here because volume sample uses that kind of -1 to 1 range. It doesn't use UVs, it uses the -1 to 1, which is reflected in @P, as I talked about a second ago. From the noise image, I'm reading the R value, which is just some number between 0 and 1, remapping that to -1 and 1, and I'm using that as an offset in order to sample the butterfly image. So I'm just adding that offset to PX, and I'm using some amount slider here so that, let's see the result. You can kind of see that as I drag this up, the kind of distortion gets bigger. And okay, let's go to the next example, talk about multiple outputs. So in this case, yeah, I have two inputs coming from the same butterfly image, and in the wrangle, I'm just saying @C2 equals 1.0 minus @C. So I'm setting the second output to equal the first input inverted. And you can see that both these outputs are visible if I plug in nulls there. So the first one is just the original image, because I didn't manipulate @C in here. So it's exactly the same as the one I passed in. However, C2 is now inverted. Now you might be wondering, why do I need a C2 input if I'm only writing a C2 output? And that's kind of true. You don't actually need it, but I found something kind of interesting, which is that if I do @C2 equals @C, okay, so it does seem like it kind of works. So maybe you don't need that C2 input, but basically when you make an input in here, it creates an input node and an output node. So I was finding a little bit of bugginess if I had nothing connected in here. I'm not able to reproduce it now, but keep that in mind. So that's pretty much it for Vex volume wrangles. I should mention I did try and figure out how you can write to other pixels to do something like pixel sorting, but I don't think it's possible using volume wrangle. Unfortunately, because in SOPs you would do like a detail wrangle or an attribute wrangle set to detail. It would just do a single iteration and you could edit anything, but it's just not possible with volume wrangle, unfortunately. So yeah, so let's just talk about feedback here. So this was something that was very difficult in the old COP system. I have a video about it. It was still super hacky, even though I did find a way to do it. So it's way easier now. Basically, let me just delete this stuff because I actually had to re-record this video because there was some bugginess going on. But basically what you do to make a feedback loop is you first create a block here, and then you add an input and you add an output, and then you do an invoke block, and you drag the block end node in here, and then you set inputs and outputs from selected block. Okay. So now I can pass my file inward here, and I'm going to connect these two things. Oops. And I'm going to check the output, and it's just going to be a pass-through right now. What's going to happen is, based on this number of iterations here, which I'm going to bind to frame, it's going to just basically run it through this block that many times. It's kind of like a for each number block in SOPs with the feedback output type. So for example, if I just put in a bright in here, and I'm just going to raise the brightness by set the brightness to 1.05. So now as I go through the timeline, it's going to incrementally increase this brightness. So pretty self-explanatory, and I think there's more info if you look on this VFX Mentor Quick Tips page. There's a lot of stuff about Copernicus here. It's worth scanning through. Yeah. Not really going to show a lot about this, but that's basically how you do it. And I think there's ways you can pass in other parameters and do more sophisticated stuff. So another example here, if I, let me check this out. So if I, if I put an edge detect in there, then you get this sort of concentric growth kind of thing, which is pretty cool. It's kind of a classic feedback effect. Okay, so kind of enough about Vex. Let's talk about OpenCL. So Side Effects recommends OpenCL because it's faster than Vex. I'm not really a fan because it's kind of difficult to write the code, and also I don't really care that much how fast my compositing stuff is. I think rendering is a lot slower than compositing, like in general, so not really a huge bottleneck. But if you care about performance, then yeah, do OpenCL. So I have a bunch of kind of examples about OpenCL here. So we're just going to start off again with our butterfly image, and then we just basically put down the OpenCL node. And if you look in the signature tab, you're going to see there's an input and an output. You can set these to RGBA if you want, or leave them at varying. And then in the kernel, you have to bind your layers. So let me actually just show creating a new one here, what it looks like. So here's my new OpenCL. And if you go in the signature, yeah, there's a source and a dest, source and destination. In the kernel, there's these like question mark and exclamation mark and ampersand, and it's kind of weird. But basically, this val right here is a default value. We don't need that. Our source doesn't even need to be optional. So this question mark just means it's optional. I don't need that. The ampersand means that I'm going to write to this value, and the exclamation mark means that I'm not allowed to read from this value, so I don't need that exclamation mark. I'm not even going to read to it, but it doesn't really matter. And in my kernel here, I'm just saying at destination set source. So that's just basically copying the source over the destination, and then here you can see the output. So that's really just a pass-through. Sort of similar to the volume wrangle, the at DST is just referring to the current voxel being set. The current voxel being processed. So here's another example. In this case, I'm doing an invert. So at source set 1.0f minus at source. And I just want to point out here that you don't necessarily need separate source and destination. I can just read from source and then write to source. That's totally fine. In this case, I'm going to talk about the second input, how to combine multiple. Let's see. So in this case, I have like 2 images of different sizes, I believe. And I'm going to talk about different inputs and different outputs. So in this one, I'm setting the first output to equal the second input minus the first input. So that's going to be our noise minus our butterfly. And then the other one is going to be our noise plus our butterfly. So you're going to see that here. And then we have a source output and a source 2 output. So that's pretty easy. You get multiple outputs. Cool. So now I'm going to talk about UVs a bit. And also parameters. So first of all, if you want to create parameters, you just say bind parm, and then the parm name, and then the data type, and then you press this button, and then it just creates these little sliders up here. What's going on in here? So similar to the volume wrangle, we have IX and IY. We also have XRes and YRes. And I want to mention, it's probably worth looking at this OpenCL for Vex users article here, which talks about some of the stuff available to you. I mean, it mentions IX and IY somewhere in here. I think right here. Yep. Global bindings. So I'm reading the position and IX, IY, the resolution, and then same as before, UV is just position divided by resolution. Here I'm doing a bit of manipulation on the UVX. And then I'm bringing that back into the IX, IY space by multiplying it with res. So we're getting voxel index again. And then to read from that other UV coordinate here, I am using buffer sample, source.buffer sample, and I pass it a float2 or an int2 also works. I was finding float2 was working a bit better. And then I just use source set to that value again. So this is how you read from other coordinates, basically. And I do not know why there are these weird little artifacts going on in here. That's a little bit weird. I don't know what the deal is. So yeah, let me know if you know about that. But just kind of an example here. Let's talk about UVs again. So here again, I have two images. These are different sizes. And in this case, I'm just kind of raising the point that you're going to need to convert your coordinates to UV space and then convert them back into voxel index space or pixel index space in order to sample it. So this first image output is just basically the second input. So this noise, sorry, these are actually bricks, I think. These bricks are getting copied over to the first output. The butterfly is getting copied over to the second output. The third output, though, is going to be right here. So we do the brick image buffer sampled according to IX and IY. But IX and IY are being actually referring to the butterfly. And since the butterfly image is smaller, we end up getting this kind of weird incorrect result. So what we need to do instead is first convert IX and IY into UVs, and then multiply them by the source 2 X resolution and source 2 Y resolution in order to basically shrink this brick image into the same size as the butterfly image. That was sort of a mouthful, not really super important, but just recognize that if your images are different sizes, you're going to have to do a little bit of UV manipulation stuff. You have to rescale your UVs, kind of. So anyway, is it possible to write to other pixel values besides the one you're processing? In OpenCL, yes, you can. And here's an example of that. I actually have this in HTA, so I'm going to dive in here. Now this is running, so give it a second. It's doing pixel sorting. It's slow, as you mentioned, very slow. Come on. Okay, there we go. So basically what I'm doing here is something like a detail wrangle. And the way I'm doing this is if you go to the options tab, you set this tile size to be the same as the resolution. So it's basically going to run this kernel once for the entire image, and you can read and write from any pixel. So in this case, I just have this pixel sorting code here, but you can see I'm looping through the X resolution and the Y resolution. And then ultimately I'm using set index, which lets me set the value at a specific XY position with a specific float 4 value. So yeah, the mechanics of how I'm doing pixel sorting here aren't really that important, but I pretty much got this from ChatGPT, but you can set other pixel values this way and use buffer index again to read from other locations. You can also do feedback inside of OpenCL here. Yeah, so what you need to do here is check this use writeback kernel. And now I'm going to have I'm going to have a source and a destination input and a source and a destination output. Inside my kernel, this is a pretty simple one. So I also have a noise, which is sort of a static input here. But what I'm doing is I am basically reading the noise value, and I'm using that as an offset when I sample the source image. So that's just doing some kind of manipulation on the source image. But then most importantly, in this writeback kernel here, I'm saying at source set destination. And I think this is probably all you're going to need for most writeback kernels. It just takes the output, sets it back to the input. But if you go to the options and then there's this iterations number, just bind this to $F. And now when you kind of scrub through your timeline, you can see it's producing a feedback effect, which is cool. Yeah, that's pretty much the gist of it. I think this is probably faster than using it in Vex. But then again, you have to write OpenCL, which is not the most fun. Okay, so let's talk about Python. So you can't actually use Python inside of COPS. You have to bring your COPS into SOPs, write your Python there, and then bring it back into COPS, which is actually easier than it sounds. So I just have this butterfly image here. Note, importantly, that this is channel type mono right now. I'm doing this on purpose. So now I have a SOP import, and this is similar to like the SOP create in LOPS. So if you dive into this, you actually have a SOP net. And in here I have another COP.NET, but this isn't a real COP.NET. It's actually empty, and it just references that butterfly input here, checking the use internal cop input, and then you type in that path. So now if I visualize this, let's go to the scene view, and you see I have my butterfly. And at this point, if I middle click here, you can see I have a volume, 512 by 512, and it has a vec4 type, which is strange. I thought that would be a float. Yes, it is a float, sorry. If you see here, now it says float. So that's because it was mono, so now the volume only contains a float. So in our Python node here, we basically just use who.pwd to get the current node, then you get the geometry, and then use .prim to get the volume. You get the resolution from the volume, and then here I'm just looping through basically every coordinate using xres and ys, and then I'm going to use volume.voxel and volume.setVoxel to read and write it. So you can go to the Python docs for who.volume to see these functions. And the reason it's so important that that was a mono input is because the voxel and setVoxel functions accept floats. So voxel returns a float, setVoxel takes a float. So there's a workaround for this, so you can use Python and RGBA images, but this example is just using floats. So I'm reading the coordinate using volume.voxel, and I pass it a XYZ coordinate. In this case, the Z is always 0, so that's hard-coded. And I'm saying here that if the value is greater than 0, meaning it's not a white, it's not a black pixel, then I'm setting the output to be white. Otherwise, I'm setting the output to be 0. So now if I go back to cops here, you can see I can't actually see if I can visualize the SOP import here, that's fine. But it's a geometry, so if you want to get that back into like an image layer, you have to use geo to layer. It's pretty straightforward. So and make sure this signature matches what you're outputting. Okay, so let's talk about RGBA. And I have an HDA for this, so I'm not really going to be building this all from scratch, but I'm going to be showing you the concept of how you can use Python on RGBA images. This is actually a pixel sorting example, so if I go forward in the timeline here, say to 25, you can see it's going to basically should be pixel sorting. Okay, here we go. I need to go up here. Pixel sorting the image. Yeah. And you see if I go through the timeline, it'll pixel sort more or less of the image. You can kind of see it sorting over time if you render out a flipbook. But anyway, just kind of don't worry about the fact that this is an HDA. It has some kind of utility stuff, so you can write your script in here and not worry about the internals, but I'm just going to show you kind of how it's built. So it's basically the same thing. I have my input here. Again, don't worry about the fact that there's multiple inputs. Really, this works with just one input. So have that, and then you have your SOP import here, and then it's just like allow editing of contents here. So yeah, we have our kind of cop input. Now, since this is RGBA, if you middle click here, you can see it's a vector4 volume. So if you go to the geometry spreadsheet, you'll see there's still only one primitive, and that's the volume. But in this case, it's vector4 type, which means that we basically cannot use these voxel and set voxels to get the colors out. So what we actually need to do is split this volume into 4 volumes. So I have a utility HDA called split volume. What this does is it takes our input volume and then it makes 4 other volumes, which are the same size. And then it uses volume wrangles to use volume sample P. So volume sample P, I think I mentioned it. Yeah, it reads a vector4 from the volume. And then it just extracts out the red component, the green component, the G, and the B, and the A. And then it's going to merge this all together. So what do I have here? I have 4 volumes, 4 primitives, and each of them is containing floats. So that's how I'm taking my vector4 volume and splitting it into 4 float volumes. Okay, so now I have my Python code. So let's take a look at this. Essentially, what I'm doing here is whenever I want to read a vector 4 value, I have to read from all four of those float volumes, and then combine the result into one vector 4 value. And if I want to write, I have to split out the RGBA of my vector 4 value and then assign each component to the respective float volume. So that's basically what these utility functions here are for. You're welcome to read through this, but this is sort of just some I don't know, utility stuff to make this a bit easier. And then at the end of the day, you still have 4 volumes, so you need to use a merge volume to bring them back together. This is pretty simple. You just kind of read from all 4 float volumes, and then you write the value out to a vector 4 volume. So now you have one vector 4 output. Yeah, that was kind of a mouthful, and I can make this Python cop available if you just ask for it. I'll totally give that to you. But that's pretty much it for now. Hope this was useful. Thanks.